Hello, everybody. Welcome to our talk, Unified and Elastic Batch and Stream Processing Stack with Pravega and Apache Flink. This talk is given jointly by Flavio Junquera and me, Flavio from the Pravega project, me from the Flink project. And yeah, we're going to talk about Unified Batch and Stream Processing. Flavio is coming in a second, he's still getting geared up. All right, we have quite a bit of contents today. I hope you bear with us for a while. In order to get started, let's quickly talk about batch and stream processing. Or maybe let me start slightly differently, because I think we actually have something very interesting here today. You probably noticed that there's a lot of talk about stream processing recently. Stream processing becoming one of the quite hot topics. As stream processing becomes quite hot, there's also very often the claim, stream processing is actually the cool new paradigm. It's the superset of batch processing. If you do stream processing properly, you don't need batch processing anymore. At least if you have a system that does this unified batch and stream processing. So this vision is all out there. But honestly, it's a very hard thing to make this work in practice beyond the theory and the simple use cases. For a variety of reasons, just certain building blocks just missing to make this whole vision reality. And I think here, with this stack that we're presenting here, I think this is kind of the first stack out there that can actually make this idea, this whole vision a reality. Parts of that, work very well today, and then there's also an outlook on how this thing will develop in the future, which we're going to talk about today. All right, just to set the stage, when we say batch and stream processing, what are we actually talking about? And the way I like to think about this is to start with that question, to kind of think about batch and stream processing. What changes faster? Is it your data or is it your query? If you have a sort of static set of data or a slowly changing data set, and you have a lot of fast different queries, then, for example, thinking of, you have a dashboard tool that you use to explore a data set. You do a machine learning training, you run a very different queries or a very different training models for different parameterizations over the same set of data. Versus you have a continuous application that is long living, same business logic, just data coming and updating, either every second, every hour, or every day. If you have the left-hand side, you have a batch processing use case classically. Sort of static data set, a lot of queries. The right-hand side, kind of continuous application, logic is fixed, data changes, stream processing use case. Now you can actually see that this is a very broad definition of stream processing, right? It includes a lot more than what many people may initially think of stream processing, just like real-time event processing, maybe some fraud detection, some real-time dashboards and so on. This is actually way more. It's in some sense everything that runs continuously. It includes actually, if you think about this definition, it includes nightly batch jobs and all of those things. So that's what we think of stream processing, continuous applications. Streams being the unifying paradigm behind all of this, right? A stream just being something, some sequence of events that is produced. It starts somewhere, it goes on potentially infinitely. There's some point now where new events are being produced. There's the history of events, and anytime you slice a bounded set of events, what we call a bounded stream, right? This is kind of a static data set. This is something on which you can do batch processing. If you don't bound it, then you have an unbounded stream, kind of the more stream processing use case. And sure, bounded streams can also start in the past and terminate some point in the future. Unbounded streams can start now and go in the future. Pure stream processing, okay, they can start in the past, make their way all the way through the past, go into the future, which is kind of stream processing with what we often call bootstrapping. So you do process, let's say you're training a machine learning model, you're processing all the events from the past in order to train the model, and then you're reaching now, and then you're processing the live events to evaluate the model and keep updating it. So kind of stream processing with bootstrapping. If you start to really embrace this paradigm, the really nice thing about this is it kind of gives you a unified view of handling a lot of different use cases. There's, of course, the classical real-time data stream processing, real-time analytics. It gives you a handle at batch processing as well. Batch processing as, bounded data streams, static historic data, and it gives you a handle of doing event-driven real-time applications, like fraud detection applications, or, you can go actually crazy if you embrace that paradigm properly. We've seen an entire social network being implemented on top of a stream processor. You can carry that paradigm pretty far. Now, the main part of this talk, the quest for unified batch and stream processing. What makes this so challenging today, and what do we actually bring with this Flink and Pravega here? Why is this an interesting stack that actually answers some of these questions from before? Let's just look at a few of these use cases. Some pure batch use case, some pure streaming use case, and some mixed use cases like stream processing with bootstrapping. Let's take an SQL query that queries some data from the past, some timestamps that lie in the past. So we're slicing a chunk of events from the past. How would you execute that today? It's probably pretty straightforward, right? You use a batch processor or a capable stream processor. You connect it to some bulk storage, S3, HDFS, GFS, a database, whatever, some bulk batch storage, and you just run the query. So far, so good. That's actually how it looks like, right? You have your batch processor, your storage. You do all these things like open all the different file streams to the HDFS blocks or query different ranges from the database, scan different chunks in parallel. And then you process it, optimized for processing finite data. If we look at querying the future, right? So we have something that's a pure stream processing job. Same SQL query. The only thing is we're not using a time slice from the past, but we're using something that starts now and goes into the future. Pure stream processing. All the new events that come in update the result. How do you actually compute this today? Probably using a stream processor and connecting to some form of pub subsystem, right? A stream processor that doesn't have to gather all the data till the end because there is no end, but one that just takes events incrementally and computes results to the SQL set. And you'd connect this to Kafka, Kinesis, PubSub, whatever your favorite message queue is. Something like that. Now, if we actually look at querying the past and the future together, this becomes a lot more tricky. Let's say we're starting somewhere here, way in the past, maybe over a year, and we're saying we're running a query that starts here and then becomes a live query and goes on and on and on. How do you actually do that? That seems quite tricky. What do? Use a stream processor? What stream processor is actually good at processing massive amounts of data from the past really efficiently, but also being able to do real-time work? And where do you actually get all this data from, right? I mean, data that's over a year old is typically not in your pub subsystem anymore. I mean, some systems do retain data for a while, but try to keep more than a year's worth of data in Kafka for a really serious use case. It's not that easy. So some part is in a file system, some part is in a pub sub. How do you actually manage to do that? So this is kind of where the whole story of unified batch and stream processing obviously breaks. Because what you actually need is if you want to make use of that today, you kind of need a dual source, right? Some old data from a file system that you probably want to read massively parallel because it's a lot of data. Some data from a real-time system that you receive with low latency, and then some system that can sort of handle both of these paradigms efficiently. All right. So when building a unified batch and streaming stack, there are three parts that we start to think about. There's a unified model, an API, that allows you to just describe your application in such a way that it makes sense on the historic and the real-time data. There's a storage that can actually give you the same view on historic and real-time data and the same access. And then there's a runtime, which is able to guarantee both performance on large historic workloads on large sets of historic data as well as on real-time data. So this stack the way we're presenting this today is actually this combination of Pravega for a storage system and Flink for a processing system. And we're going to go through the aspects of those two systems now. So let's start with the Pravega side. Flavio, please.
All right, thanks, Stefan. I'm Flavio. I am, sorry for doing the introduction in the middle of the talk. I'm a director at Dell EMC, and I'm also the lead engineer for Pravega. So let me tell you a bit about Pravega in the context of what Stefan just motivated and described. Obviously, we believe in this unification of batch and stream, and that's part of the reason we are even doing Pravega. So Pravega is a storage system for storing streams. So stream is a first-class citizen, a first-class primitive of storage in our system. It's a young project. We haven't completed 2 years doing development, and it's under heavy development. We have decided early on to open source it, so I highly encourage everyone here to go and check, our website. There's a lot of information about the project itself and our GitHub repository that has the source data and where we do all our development today. Streams in Pravega. The way we see streams in a similar way that Stefan was describing, we have a present for a stream, which represents all the data that you have ingested, that you have stored for the stream. Then you have what really depends on the application, but some notion of recent past, which is fresh data that you might want to process with low latency. This could be seconds, minutes, I don't know, hours. It really depends on your application. And then what I'm calling the distant past, which is a lot of stuff that you have ingested a long time back, but you still want to keep around. You might want to process that again or in a different way, so you still want to hold to that data. And today, we tend to store these things separately. Like this recent past goes into some messaging, some pub sub, think of, I don't know, RabbitMQ or Kafka. And that other part goes into some bulk store. I don't know, maybe HDFS, Cassandra. And one of the key things we want to do with Pravega is to actually unify that. We want to give you a unified view over the data. So you ingest stream data, and the data stays in Pravega, and the API to access the data is always the same. But it's not only about unification. So Pravega is about other things as well. As part of being able to ingest the data and hold on to that data for a long time, we gotta be able to store an unbounded amount of data on a per stream basis. So it's very important in whatever architecture we come up with to be able to store an unbounded amount of data per stream. Because we'll talk about stream processing, you can have applications where you have cycles. You have daily cycles, weekly cycles, I don't know, seasonal spikes. And you might want to adapt your ingestion capacity to the rate you're observing out of your workload. So that kind of accommodating these changes to the workload is also one of the key goals that we have in Pravega. Starting from the very basics, when we work with Pravega, if you to ingest stream data, you append it to a Pravega stream. To process stream data, you read it from a Pravega stream. When you look at the API, these are the concepts that map into what I just said. So you have event writers that write events to Pravega streams, and you have event readers that read events from a Pravega stream. We group them in what we call a reader group, and we have such a group so that we can balance the load of reading across a number of readers, and so that you can make it scalable as well, so that it can grow and shrink according to demand. When we look at what's actually happening on that write path, when the event writer wants to append data to the stream, the first thing he needs to do is to determine which server he needs to talk to. So the servers are called segment stores. It will be clear in a few slides now why I call it segment store. So it gets from the control plane, from the controller, which server it needs to talk to. It connects to that server. It sends its request to append bytes. That segment store is going to make a write to tier 1, which today is implemented with Apache Bookkeeper. And it only returns to the event writer once it has durably stored in Bookkeeper. So we use Bookkeeper here because we want to make that path optimized for low latency durable writes. Now we have a second tier, tier 2, to which we do not write synchronously. So we move the data asynchronously from tier 1 to tier 2. And the reason for having this tier 2 option is because we want to have a high read and write throughput option when reading and writing the data. For writing, because we want to keep up with the write path here, and for reading, to be able to cope with historical and catch-up reads. Some of the important guarantees on the write path, we guarantee order according to the application, according to the calls of the application, and specifically end-to-end, we guarantee per key order. We avoid duplicates by using writer IDs. The writer IDs, they map to the last events written for a given event writer, and that is persisted in the segment store. And this is essentially part of our story for exactly one semantics on the write path. So we use the duplication via writer IDs, but to be able to cope with crash failures of the writers, for example, we need to use something else, which is transactions. I haven't talked about that. I'll talk about it a few slides down. But that's sort of some of the key concepts that we have on the write path. The read path is very similar. So the event reader needs to get the server from the controller, talks to the server. Server has a cache. If the data is in the cache, it just returns. If not, if it's a cache miss, it pulls the data out of tier 2. And so mapping to the figure, or actually not there yet. So I must say that in tier 1, we never read data from tier 1. We never serve data from tier 1 directly. The data in tier 1 is there for recovery purposes. So essentially use that as a journal to make sure that we can recover from crashes. And so now mapping to the figure that Stefan was showing before. So the way we map this is the recent pass should be served from the cache of the segment store, and cache misses should be served from tier 2. So where we have our long-term storage for data, for stream data. Now let me talk about one very key concept in Pravega. This is very important to understand why we can do a lot of the features that we offer and a lot of the features that we want to provide in the future. So a stream in Pravega is composed of segments. Segment is very simple data structures. A pen-dogging data structure stores a sequence of bytes. Now, with the segments, we can do things that we have already seen in other systems, like we can put segments in parallel in a stream and have event writers writing in parallel to those segments, using a routing key that is provided by the application so that we can guarantee per key order. But and segments, one interesting characteristic of segments in Pravega is that they can be sealed. Now, when you seal a segment, you can no longer append to that segment. So if an event writer tries to append to that segment, it's going to get a message back saying that it can't. Now, you're probably wondering, so why do I care about sealing segments? You might not care about it directly, but it allows us to do a number of cool things in Pravega. So I can start, for example, from one segment, populate it with data, then seal the segment, start a new one, populate it, seal it, start a new one, and so on. And I can call this a stream, right? So this can be a stream. And in fact, I can do this an unbounded number of times. I can have as many chunks like that as I want, and call it a stream. And this is nice because I am not bounding the capacity of a stream to the capacity of a single server. I can store each one of the segments in a separate server if I want. So essentially, I'm giving the potential of storing, of using the whole capacity of a cluster for a single stream. I'm not saying this is a wise thing to do, but architecturally, I'm providing you with that possibility. But it's not only this linear composition. I have already talked about parallelism, so I can have parallel segments, decide that I want to seal them, create a new one, and have just a single segment. I could do that because I don't need 2 segments, I only need one. So those are things that I can do and form streams that way. But this is a bit abstract. What are some useful features that I can provide by composing segments that way? One is scaling a stream. Remember that I mentioned that I wanted to adapt the capacity, the ingestion capacity, according to the workload. So this is something I can do this way. So if I have a segment, at some point I determine that the segment is hot, so I can seal it, create 2 new ones. And assuming that they live in different servers, I'm giving more ingestion capacity to the application. And this in Pravega today can be done in 2 ways. It can be done automatically. You can set up a stream so that Pravega does it for you. Or it can also be done manually if you decide that is best for your application. To illustrate what actually happens, or what we expect to happen with a stream, so this diagram here shows time, elapsed time versus the routing key space. So this is the entire routing key space that is mapping to the segments. So if I start again with a single segment, I can have at some time t0 that Pravega decides, you have set auto-scaling for this stream. Pravega decides that it's time to split at that point, it goes and executes the procedure for scaling the stream. So it splits the routing key space into two new segments, 2 and 3. But note that I'm signaling two hotkeys here, which are mapping, which turn out to be matching to this to segment 2. So splitting it into segments 2 and 3 was not sufficient. And so at another time T1, we do a new split of 2 between segments 4 and 5. And so again, the routing key space is split from half to half of the other half between 4 and 5. Now, if those keys become no longer hot, the other thing I can decide, Pravega can decide, is that at a later time, T2, it's time to merge those back into segment 6. So this is the kind of dynamics that we expect for a stream, for a real application. And one thing that you might have noticed is that the mapping of the routing key space to segments is actually not constant. So it's not statically defined. So when I create a stream, it might be mapping, so the range might be mapping to one set of segments, and as the stream evolves, it maps to a different set of segments. It really depends on at what time you're talking about. And you disambiguate it based on the information in the control plane. So the controller does that work of informing the clients what is the right set of segments to work with. This figure is actually a more realistic way of seeing what, of visualizing what I have just described. So here, what I'm showing is a heat map where I show the state of segments. So light blue corresponds to light load on the segment. Bright red means that the segment is heavily loaded. And the white just corresponds to the space between segments, just splitting segments. And so what we observe here, coming from the left, we have some segments here. They start merging down to a minimum around 5 a.m., which is 2. We have actually set it to be 2. And then at some point, they start splitting again. If you think about what's going on here, it pretty much feels like we have some traffic here. It's cooling down to a minimum at this point, and then it's picking up again. And this is exactly what's happening. So we used this data set, this workload, to actually generate that graph. And this is from this New York City yellow text strip records data set. We got 1 day, actually we got 12 hours to show this. And we have from left some workload, then drops down to minimum around 5 a.m. and then around 6 a.m. it starts to pick up again. Putting those together, this is what we observe. As we have traffic, you have more segments. As it goes down, fewer segments. As it picks up, it goes up again. So this is what we observe here. All right, so that's what I had to say about autoscaling. Another feature that we can do with this flexible way of managing segments is transactions. Transactions provides you a way to write a set of events in an atomic manner. And the reason why this is interesting in Pravega is because we have this cheap way of creating segments. And so when we begin a transaction in an application, we create transaction segments. And only upon merge and abort, we do something with those segments. To make this more concrete, so if I have a stream with 2 segments, application begins transaction. Pravega is going to create 2 transaction segments, each one mirroring the one of the primary segments of the stream. Any write in the context of the transaction goes to the transaction segments, like in steps 3 and 4. At step 5, the application decides to commit. So I have done all my writes, so it commits. When it commits, the segments are sealed so that it makes sure that the state in the segments is consistent, so nothing else can go in at that point. And at the last step is actually merging that data onto the primary segments. And then at that point, the data is visible. So this is very interesting because I'm not interfering. Note that because I'm doing writes on separate segments, I'm not interfering with the writes in the primary segments. And the other thing is, if the application decides to abort instead of committing, I can simply drop those segments. and there is no trace of that data, I'm not leaving any sort of dirty data in the system as a consequence of aborting. A third feature that we can do, and this relates to what Stefan was mentioning before, so the possibility of doing ordered versus unordered reads, is that because I am storing data for a stream in this manner, like I start with one segment and then I split into two segments and so on, it doesn't necessarily mean that I have to follow that order. We do if the application, if that's what the application wants. So of course, we give you that possibility. We have the metadata to follow the order of the creation of segments. But again, we don't necessarily need to do that. We could expose all segments in parallel. In fact, we do. We do have an option in our clients that allows you to read from all those segments in parallel. In that case, you're getting, again, unordered reads. You should know what you're doing, but you know, it's an option that you can choose from between reading as a stream and reading in an unordered manner or in parallel. All right, so to wrap up this part, let me try to put it all together in one example. Remember some of the concepts I have mentioned. Event writer, perform appends. They can be transactional, but let's focus on regular appends for now. And on the reader side, we have event readers organized as a group. They coordinate to do the assignment of segments. I didn't mention this before, but we have this nice facility called the state synchronizer that allows you to synchronize state across processes. And we both expose it through our API and also use that internally in our implementation of the reader group. And one of the key features that we provide through reader groups is checkpointing, which is key for Flink to provide exactly one semantics. Now, if I have a stream with two segments, I can have event writers appending to them, right? Appending events to them. And on the reader group side, I can have an assignment that is, you know, segment 1 to reader 1, segment 2 to reader 2. And they will be reading the segments as they come. They'll be trying to tail up those segments. Now, at some point, if autoscaling is enabled, Pravega might say, well, segment 2 is hot, so we need to scale up. It's going to seal segment 2, and it's going to create two new segments, segments 3 and 4. Once that happens, the event writers can start writing to those segments. So they might have tried to append to segment 2, and it's sealed, so they found out that that they need to append to 3 and 4. So they can already start appending to 3 and 4. But the same doesn't happen on the read side, because if I start reading from those segments before I finish reading from the segments, I might be violating key order. And the event reader that is assigned segment 2 has only read the green events. And by the way, I'm using color to represent keys here. And so before the reader group goes into reading these two segments, we need to finish reading segment 2. And so once that happens, the event reader will find out because it has hit the end of the segment. You know, it finds that it's sealed. So it requests from the controller the successors, which are 3 and 4, and adds them to the set of unassigned segments, which is part of the reader group state. Then the reader group coordinates, and they assign 3 and 4 this way, 3 to reader 1 and 4 to reader 2. And from that point on, they can start reading the events. Now, if Flink, let's say, comes and initiates a checkpoint as part of doing its own checkpointing, what's going to happen is the reader group is going to make each reader emit a checkpoint event. So that is supposed to indicate that there's a checkpointing going on. And for any process in general, it should do its own bookkeeping, if anything at all. In the case of Flink, it's going to trigger the whole checkpointing processing downstream. And once that happens across all readers, it delivers a checkpoint object, which contains the offsets of the segments. And with that, if Flink needs to, it can roll back to that particular point. And so with this part, I actually conclude the description on Pravega, and I pass the word back to Stefan to talk about APIs and execution.
All right, thanks. I'm going to give a very, very brief introduction to Apache Flink, and then go a bit more into the unified and batch and streaming and integration with Pravega. So, just in a nutshell, Flink is a system that does stateful computations over data streams. So it consumes streams from real-time stream pub/subs, databases, storage, computes, and produces calls into applications, data for databases, result streams, or puts data into file systems. It's built after the idea of everything streams internally. So it's really data moving all the time. It has internally also concepts to handle bounded streams, kind of with certain optimizations, but always the ability to process everything as unbounded streams. No boundaries internally, like mini batches or transactional boundaries. It's purely data moving and streaming all the time. You use Flink usually through one of its layered APIs, the most prominent one being the DataStream API, which gives you the concepts of dealing with streams and windows. It has a lower level API, which is, I think, especially useful if you try to implement more complex business logic that has a very special treatment of each individual event. When you're really interested in treating individual events, let's say these present a transaction, you have to decide whether it's a valid one or a fraudulent one. Versus the DataStream API is often useful if you're more interested in aggregates of the streams, like counts, sums, averages, windows, and so on. And then there's an even higher level language, which is streaming SQL and dynamic tables, which gives you a way to declaratively express what you want to do. Just to give you a rough feeling of what it looks like to write an application, it's usually it's a fluent API, like these systems do today. You start by defining sources, doing transformations, grouping, windowing, aggregations, adding sinks. In the end, you have a flow of transformations. The SQL API, it looks actually pretty much like we showed in the example. It's an interpretation of SQL, not on static tables, but on dynamic tables. So it becomes a continuous execution of SQL, which kind of works after the paradigm of materialized view maintenance. When the input table changes, it computes results to the output table. This is actually a fascinating topic in itself, but it's a bit out of scope for this presentation. And it's actually being used very heavily at quite large scale. So it's powering a lot of streaming ETL, analytics, and machine learning in many big companies today. All right, just so much for Flink 101, very high level. Looking at unified batch and streaming from the API perspective, and going back to this notion of more batch processing use cases versus stream processing use cases, static data versus continuously changing data. If you know Flink a little bit, you know that there's kind of two APIs, the DataStream API and the Dataset API. The DataStream API being built to handle both bounded streams and unbounded streams, even if they're not explicitly called in classes like that, but it's able to actually handle bounded input and unbounded input. And then there's also the Dataset API, which you can think of as kind of a special tool for bounded streams. And I think this actually tells us implicitly quite a bit about what is the state of batch and streaming still. And it's not just an artifact in us not having made the data set like a Java subclass of a data stream, a bounded data stream. But there's actually good reasons for this to be like that still. And this kind of also gives us an idea of where the space could go in the future. There's one thing that's very inherent to stream processing, which you don't have in batch processing from the application perspective. And that is, in stream processing, you're always trading off latency versus completeness, right? You're processing events, and events come out of order, and they come late. And let's say you're computing, an average for 5 minutes of a sensor rating, and it's a disconnected sensor, so it's not always necessarily live. You're always within this kind of trade-off. I could wait just for a little longer. I might get some more delayed or late events, and I could get a better result. But also then my result is a little later, and maybe I don't want it to be too late. So I've also have this latency concern, right? And trading off this latency versus completeness is, I think, one of the absolute key things in modeling, an unbounded streaming application in many ways. If you're familiar with Flink or the Apache Beam project, that's what usually is captured by the watermark or Flink's internal event time clock. And as data arrives on time or late and so on, like this watermark captures this queue between real time and event time, where event time captures kind of data completeness. Now, that is something you inherently don't have to do in batch processing, right? Because you're starting with a data set, and that data set is as complete as it ever gets within that batch job. So you can think of stream processing versus batch processing. If unbounded streaming, you have to have the ability to include this trade-off between latency and completeness. And in the batch job, you're always assuming that your data is as complete as it gets, no concern about latency. So you're sort of implicitly just think of the system just throws the switch completely to the completeness and to the non-latency side for batch processing. If I go back one level, that is in some sense exactly what happens. If you have the DataStream API, for example, operating on bounded streams and not you typically don't generate watermarks at all, so you're basically just computing everything as one complete go. You throw the watermark at the very end, and then you have a complete result. And the dataset API is almost like a special case where it says we're basically excluding this as a configuration parameter because we don't need this on bounded data sets. Now on the execution side, there's also a slight change still. I mean, doing this API unification is, I think, kind of a well understood thing by now. So Flink has done this in its APIs, Apache Beam has done this in its APIs, the effort of streaming SQL has done this very well. Where I think we still need to go a little bit further is the runtime. Let's quickly talk about the state of the art. What does Flink do internally to do the unified batch and streaming execution? So the first very important design primitive internally in Flink is streaming data flows for everything, right? For batch and for streaming. There's no micro batching, there's no transactions, because that kind of breaks the whole paradigm. Parallelized streaming data flows. If we look at how Flink does fault tolerance, that is also an absolutely essential thing in the unification of batch and streaming, right? You may remember that I said initially the paradigm of Flink is initially to just keep data moving all the time. There's no batching, there's no transactional boundary, so it's just a stream that flows, and that is important. Because first of all, it gives you really end-to-end low latency without adding up micro-batch boundary latency or transactional latency, and it also gives you the performance that you need actually to do the batchy kind of execution. If you work yourself through, like let's say a petabyte of historic data in order to bootstrap the work going towards the real-time side. If you try to do, like transactional handover with intermediate state replication and so on, like some pure stream processors do, it's just impossible to do this on large catch-up workloads. So you really have to do this in-memory, shuffle to in-memory kind of execution. Now, having it built like that, how do you do fault tolerance, right? You don't have mini batches to recover, you don't have transactions to recover. So Flink introduced this idea of doing asynchronous snapshots in the background, which basically capture the state of the streaming computation to fall back, just making fault tolerance an asynchronous background process. And that's actually quite a powerful mechanism, because you can tune it completely towards the batch side, where say you do this very rarely, and you just move a lot in memory, and then you go back in a slightly more coarse-grained manner, or you can do it in a very fine-grained way in streaming, like doing incremental checkpoints every second or every few seconds, and get a very good streaming fault tolerance. So it's kind of a mechanism that allows you to capture fault tolerance on both sides very well. Another thing that's actually very interesting and maybe not really obvious immediately if you do batch and stream processing that you do it slightly differently from both the processing and the I/O perspective. If we're in the DataStream API, Flavio mentioned this originally, what you typically do is you process data in a stream order. So we started with a segment, we split it, we merged it together. So you kind of have to read the data like this if you're doing proper stream processing. And that makes sense, because that's also how the segments are created in real time. If you actually do a lot of catch-up work, or you process a lot of historic data, actually reading the data like this is not what you typically want to do, because it means during that phase you can read with a parallelism of 1. You can read with a parallelism of 2 here, and you can again read with a parallelism of 1. If that qualifies for a long historic, if that is true for a long historic span of data, then you're just going to take forever just by virtue of not being able to parallelize the processing, or at least the I/O side of things very well. Now, what the dataset API does, for example, it just flips this thing around and says, okay, I just read everything in parallel out of order. I'm applying a lot of batch bulk transformations to sort it, bring it back in order, and then just process it in one go, which gives the ability to just parallelize historic reads way more than if you do pure stream processing. All right, there was just very briefly on the model and execution side. There's a bit of an outlook where we actually want to take this later, or a quick wrap up. If you stay with us for a few more seconds, I think there's some thoughts ahead here. So there's a good amount of work in the unified batch and stream processing world going on. I think on the API side, I would say this is pretty much done, right? We have done this in multiple projects, Flink and Beam, both on APIs and on the SQL side. And it just turns out that batch processing is really a bounded stream with some simplifying assumptions. You don't have to. You can kind of deactivate the knob that is the trade-off, the latency completeness trade-off, right? Flavio has shown that there's a way to do this extremely efficiently on the storage side as well, with Pravega being an implementation for that. I would say that the runtime is still the most ununified piece that is out there, and that is pretty much true for almost everything. Even if you look at things like running Apache Beam on Google Cloud, there's two separate runtimes for batch and stream processing. If you go to Flink, there's still different operator implementations for batch and streaming execution, like for bounded and unbounded execution. And a lot of this just comes down to in-order processing versus out-of-order processing. But there's also a lot of potential to get those together. And let's skip this for the sake of time. Let's just use this as a use case, right? The state bootstrapping use case. This is actually not an esoteric use case. It's actually one of the ones that has come up again and again and again from users that have adopted stream processing and are starting, after a year or so of adopting it, are trying to take it to the next level. If you do these queries that start way in the past and go into the future, it's a really desirable thing to actually say we do batch processing for the first part and then switch to stream processing. Meaning what you would actually do, going back to this work that we presented before, you would actually try to break this one up and do parallel reads in the past to streaming reads over there. So kind of split the whole processing there, chop it off into a system that reads in parallel there and then goes on kind of streaming sequentially or ordered in the future. So that's kind of the next step, I think, for the batch and streaming unification. I think once we've implemented that, we pretty much have a very round story there. And yeah, I think this is then the pieces that will actually allow this whole idea of stream processing, subsumes batch processing, real-time processing, historic processing, and combinations thereof that can really bring this vision to a conclusion. All right. Thank you very much. Sorry for taking over time. It was a lot of contents, but thanks for staying with us.